Jai Hind and everyone. I am Anupam Kumar Saini, IT department, Akgec Ghaziabad. Today I am discuss Euler graph. That is important for second year student of CSE, IT and CSIT students. In previous class I discussed about various types of graphs. First of all I recap that points, then go with Euler graph. As previous lecture, I discussed about the application of graph, definition, terminology, types of graph, subgraph, bipartite graph, planar graph, and Hamiltonian graph. Today's topic is Hamiltonian and Euler graph. At previous lecture, I discussed about the loops, multiple edges, directed graph, handshaking lemma, introduction of graph theory, simple graph. One of the topic is simple graph. I discussed about the simple graph is a graph in which there is no loop and parallel edge. Then graph is known as simple graph, as shown here. U, V, W are simple graphs. Multigraph, in which parallel edges are allowed, then graph is known as multigraph. As shown in E1 and E2, two edges are parallel to each other. That means there are common vertices between two edges, then these edges are parallel edges. Are common between E1 and E2, then E1 and E2 are parallel edges. Directed graph, if there is a direction between each edge shown, then the graph is known as directed graph. Undirected graph will be if there is no direction, then graph is undirected graph. For example, A, B, C are three vertices, and this graph is known as undirected graph, and this one is directed graph. Weighted graph, if there is weight assigned between two vertices, then the graph is known as weighted graph. Here every edge have a weight, means we can say that distance from B to C or weight from B to C. This is weighted graph. Complete graph. Complete graph represented by Kn, symbol Kn used for representation of complete graph. Here example are K1, K2, K3, K4, K4 are complete graph, means complete graph are those graph if all the vertices are connected with remaining odd vertices, then graph is known as complete graph. For example, this graph is K4 and vertex A, B, C, D. These are four vertices A, B, C, D, and each vertex connected with remaining all other vertices. Then the graph is called complete graph. Then if between each edges we start from one vertex and end with the same vertex, reach with same vertex, and this form a circuit, then this is called cycle. Start A, B, C, D and A. Obtained by adding additional vertex between any diagram, vertex to Cn, and connecting all vertices to new vertex, means these are, if this is a graph of 4 vertex A, B, C, D, that is known as if a graph A, B, C, D, this is known as cycle. If we connect a vertex between these vertices and each vertex with connect with this vertex A, B, C, D, then it is wheel. Next topic is bipartite graph. Here I not go with in detail as I discussed in detail in previous lecture. So I am not go in the depth of this topic. In a simple graph G, if V vertices and V number of vertices and E number of edges, if we divide that graph in such a manner, if vertices of graph in divided in two parts and edge are divided if two part and one end of the edge go with V1 and other end go with V2, then the graph will be bipartite graph. Here for example, this is graph A, B, C, D. This is a graph G. If you divide this graph in such a manner that all the vertices are divided in two parts and each vertex are go with vertex V1 and V2. Here for example, there are number of vertices V equal to A, B, C and D. These are vertices graph V and edges 1, 2, 3, 4. These are edges E equal to 1, 2, 3, 4. If we divide V in two parts, V1, V1 we take A, comma C, V1 as V1 and B and D as V2. Then these vertices A, B, C, D divide in two parts, that is A, C and BD and known as V1 and V2. Such graph A, C, B, D. We see A to B, there is a edge between A to B and one edge between A to D. D to B, there is B to C, one edge B to C, one edge C to D, and but these are A to B edge 1, A to D edge 4 and B to C edge 2, B to C edge 2 and this one edge 3. If we see here, if we partition this graph in such a manner, then one end of edge 1 go with V1 and one end of each edge go with V2. Then this graph is known as bipartite graph. Complete bipartite graph, if all the vertices of V1 connected with all the vertices of V2, then this graph is known as complete bipartite graph. This complete bipartite graph represented by symbol K, M, N. This is the complete bipartite graph of 3 vertices and 3 vertices are there. K33. This graph is K22. Subgraph. A subgraph of a graph in which there is take some vertices and some edges of the complete graph. G is a graph where vertices V and E are edges. Then a subgraph take H in which vertices and edges. Here a graph UVW we take as a subgraph UVW and other subgraph UV, and this is subgraph. Isomorphic graph, if both two graphs have equal number of edges, equal number of vertices and one-to-one correspondence relation, then graph is known as isomorphic graph. Planar graph, if we construct a graph in which there is no overlapping between edges, means we can say that if a graph can draw in a plane, single plane without intersecting of edges, then the graph is known as planar graph. Now come to our today's topic, Euler graph and Hamiltonian graph. First we discuss about the walk, path and circuit. Walk on a graph G is a finite non-empty alternating sequence of vertices and edges with vertices and edges. I explain this with diagram in Euler graph. So directly go with Euler graph. Euler graph is one in which there is a closed and ending with the same vertex. Trial that includes all edges. To define this precisely, we use the idea of Euler trial. We explain with diagram. Here is a diagram in which there are vertex A, E, C, D, E. This is a graph in which A, B, C, D, E are the vertices and these are the edges. And in Euler graph, if we traverse all the edges without repeating any edge except initial edge, then the graph is known as Euler graph and the circuit form is called Eulerian circuit. Here Eulerian trial or Eulerian circuit is the closed trail containing each edge of graph G exactly once and returning to the start vertex. A graph with an Euler trial is considered Eulerian or is said to be Eulerian graph. In this graph, there is 7 edges and 6 vertices as shown here. First graph is Eulerian with the Eulerian circuit sequenced from 1 to 7. The second is not Eulerian graph. I describe here. If we traverse all the edges without repetition of any edge in that graph, then this graph will be Euler if we start and end point are same. Here we start with A. If we start with A and go reach B, then C, D, E, D, B, E and A. This was start and end point are same. Here this in this graph start and end point same, and all the edges are traversed without repetition of any edge. Means there is no any edge we traverse more than once, and start and end points are same, then Euler circuit form. We can take another example. A, B, C, D, E, F. These are the vertices. This is a graph. We have to show that this is Eulerian graph or not. Means this will form Euler circuit or not. If we start with A, the start point, then reach F, C, E, B, C, D, E, A. That is our endpoint. We see here all the vertices, all the edges traverse without repetition of any edge, and start and end point are same, then Euler circuit form here. Next, Eulerian path, a path that includes every edge exactly once, then it is called Euler path. A closed path is a Eulerian circuit. We see the Euler path here. Next diagram, graph 2. This is graph 1, graph 2, graph 3. If we see this graph, this is not Eulerian circuit. This graph G2 will not form Eulerian circuit, but it covered all the edges, but no end or end point and start point are not same in this graph. If we start with the vertices, write name here, A, B, C, D are 4 vertices. If we start with vertex B, go vertex D, C, B, A and G. This was start point, this one end point. Start and end point are not same here, then path, this will form Euler path, a path that includes every edge exactly once, but start and end point are not same, then it not form the Euler circuit. We observe here in Euler circuit in which graph their Euler circuit will form, then each vertex will have even degree. See here vertex A, degree 2, degree 4, degree 2, degree 2, degree 4. In we observe that every vertex have even number of degree, then there will be Euler circuit will form. if there are exactly two vertex of odd degree, then Euler path will form. We see here, and start with one odd degree vertex and end with other odd degree vertex, then Euler path will form. If we start any other vertex from in this graph, then there is no Euler path will form. We can see here, if we start with here, then stuck at this point and this edge will not traverse, then Euler path will not form. Means if we have a graph with exactly two vertex of odd degree and start with one vertex of odd degree and end with other vertex of odd degree, then Euler path will form. If there is a graph in which more than two vertices having odd degree, then that graph is known as non-traversal graph. Means in which graph, in that graph there will no Euler circuit and no Euler path will obtain. Okay, thank you.